No? All right, let's get going. Good morning, everybody. We've got a very straightforward agenda for today. Review answers for, not yesterday, Monday's problem set. Introduce today's problem set. And then you'll work on today's problem set. That's it, right? And then Friday, we return to the game of chess. So something to look forward to. Okay. So first of all, 2.2 problem set 1. Here we go. Oh, there's Lewis. Thank you for joining us. Here we go. Answers to problem set 1. Identifying all of the isosceles, equilaterals, scalene, right and obtuse triangles from the selection there. Do notice, probably the most important thing to highlight here is that the equilateral triangle is also isosceles, okay? But there you have them. Yes, you need the little triangle in front of the name. No, you do not need to have them in that order. You could have triangle EFD or triangle FED or whichever way you like it there. Order of the letters in a triangle's name do not matter. The order of the letters in an angle do. The middle one has to be the vertex. Okay, there is number 2, more of the same. Find the scalenes, the isosceles, right equiangular, and obtuse, which there aren't any. All right, next we had, here's some actual problem solving here, dealing with the sides of the triangle made of toothpicks again. Yay, toothpicks. I should just like build the whole course around toothpicks. Do you think we could do that? We could probably do that. Toothpick geometry. All right, if you have 20 toothpicks total, how many different isosceles triangles could you make? So isosceles, you gotta match 2 sides here. There are a total of 4 combinations, the 299, 488, 677, and the 866. Similarly, if you wanted to make scalene triangles, there are 4 different ones, all different sizes now. There's the 389, the 479, the 569, and the 578. And with 20 toothpicks, there is no possible way to make an equilateral triangle. Okay? You can play around with them all you want, but it comes down to 20 does not divide evenly by 3. Seems straightforward enough, right? And I really like this problem because there's lots of different ways you could go about it. You could go get some actual toothpicks, okay? Physically manipulate and move around, find different combinations. You could just draw them in. Right, and say, okay, if I 1, 2, 3, right? How many toothpicks to make the sides? You would need more than that, right? Until you get to 20. And you could see if you can find a systematic way of keeping track of the different combinations. Moving one, like, okay, if I take one away from this side to over here, and away from this side to over here, now I get 4, and then these reduce down to 8, right? And then I do that again. Or you can think it purely numerically, okay? You don't have to deal with the actual toothpicks themselves. Just think, how do I make 3 sides of a triangle, right? 3 side lengths, 2 of which have to match, and they add up to 20, right? So x plus y equals 20. How many different solutions are there to that equation? Okay? Do it that way too. Okay, and then number 7, consider the square lattice shown next as just a grid of dots. How many different triangles can you draw that all have segment AB as one side. There are 20 total possible triangles. Yes, you could draw them all in. In fact, you might be drawing many of them to determine the isosceles, the acute nature of them. But there's a really fast, easy way to determine there's exactly 20 possible triangles. Can anybody explain that to me here in chat? Or out loud, right? Anyone find the fast, easy way to know there has to be 20? Without drawing them all? No? Well, let's think about this a little bit. Let's draw a few just to get a feel for it. I have segment AB already drawn in. I need to connect dot A to some other dot and then connect that same dot back to B. And then to draw a different triangle, I would connect to some other dot and then back to B. Or I could connect to, whoops, this dot and back to B. Right? So really, I think, oops. See if this will, yeah, right? I can take this to any other dot that is not already part of the triangle. And so quick multiplication would show 1, 2, 3, 4, 5 by 1, 2, 3, 4, 5. 5 times 5, there are 25 dots, right? Does that mean I can go to, and there should be 25 triangles? Well, no, because the middle one doesn't count. I can't use A and B themselves again. I don't get a triangle. And I can't use these ones straight over here because I don't get a triangle again, right? See that? That doesn't make a triangle. That makes a line. So that whole row actually is no good. So you take 25 minus 5, and you get 20 possible triangles, one for every other dot in the lattice. Neat little trick there. All right, and then number 17 was this gigantic figure of lines going everywhere, right? Assume all of the best qualities, and you're basically playing geometry I Spy here. Okay, find a square, find a rectangle, not a square, right? Find a parallelogram that's also not a rectangle. And so you only needed one option for each of them. Many of them, there were multiples, right? ADPK or AEGJ. So your rectangle here is ADPK. So you either have this one or the whole thing, great big rectangle all the way around. Okay. And as long as you have those 4 letters, ideally in some sequence, either forward or back, you could go PKAD or PDAK. Just don't jump from P to A and then K to D. Like, that wouldn't be it, because you'd be like jumping diagonally. But there's lots of options there. I'll give you a minute to read through those. Compare with your answers. So notice that for the triangles, we have to have the symbol for triangle to differentiate 3 letters from an angle. 3 letters could be an angle, or 3 letters could be a triangle. Once you get to 4 letters, you know it's going to be a quadrilateral. Okay, there's no other thing there, right? Same with 5, 6 letters. It's got to be some kind of pentagon or hexagon. So we don't need a little symbol in front of it every time. Okay. Any questions on the level 1 problems? No. All right, then here we go on to level 2. I had another toothpick triangle problem, except this time you had 24 toothpicks to work with. How does that change things? Well, now we can get 5 different isosceles ones, similar kind of pattern going on. and 7 now scalene triangles. Here they all are. And 24 is divisible by 3, so we can finally get an equilateral triangle. Notice that this does show up as an isosceles. Okay, if you only had 4 isosceles, it's very likely you probably missed that one. Every equilateral triangle is also isosceles. Okay. And another drawing the triangles on the lattice. This time, because our AB was slanted, we have 30 possible dots, and only 2 of them are taken up, and there's no straight line eliminating any others, so it's 30 minus 2, 28 other dots we could connect to make a triangle. 8 are isosceles, 5 are right, 8 are acute, 15 are obtuse. Do not count up the obtuse ones by hand if you know the total, and you know how they reduce to being right and acute. Don't use isosceles. Remember, obtuse is angle, so you have to use angle reference. Obtuse, acute, and right will all total up to 28, so just subtract. Questions on level 2? Okay, then here is level 3. I like this one, dealing with intersecting figures. Okay. So a square and a circle touch at 1 point. Here they overlap at 2 points. There I have highlighted in blue. Here we have 3 points. This is where it does become important that you get the sizing correct, because to get them for all 4 points, you have to be able to do this thing. So if you weren't drawing them to the right scale relative to each other, you wouldn't be able to create the diagram. But I hope at least through the problem solving, drawing, some trial and error, guess and test, you would figure out that you need to draw it to a certain size to make 4 points of contact work at all. And then for the next one, we had a triangle and a circle. So fairly straightforward, 1 point, 2 points, just like the square, 3 points. Pretty easy. The 6-pointer, though, Again, the 3 points, you could do a small circle inside the triangle, that would get you 3, or a circumscribed circle, but not with the sizes given. The size given, this is the only way. Of course, it could be on any side, but it's got to be something like this. And similarly, this circle is too big to fit entirely inside the triangle, but it's also too small to circumscribe the triangle, that is to say, to go from the very tips around. Okay, I could it's a little bit smaller than that guy, so it goes through 6 points there. Okay, last call for questions on this problem set. Okay, then your task for today, tonight, and tomorrow is problem set 2, which focuses in much more on the symmetry aspect. Here we've got the folded paper. If it helps, go ahead and actually get a piece of paper, fold it, draw it, cut it out, get some scissors, make, your typical paper snowflake. That's the type of thing we're going here, but this is entirely doable without a physical prop. And I think you'll notice why I definitely had to include this question in our problem set. I mean, how could I not, right? It's me. Okay. And then we have some here about just the types of symmetries within various quadrilaterals. So work those out, and then a isosceles triangle as well. And then the last one for level 1 is this guy. I saw this and went, ooh, oh, we got to include that one, right? This is too cool. exploring the reflection, rotation, symmetry in all the different, not all, some of different types of gemstone cuts, okay? And so notice, like, this might be something you don't know, right? Emerald is actually the name of a cut of a gemstone, not just the name for a green gemstone, okay? That is as well, but you can have a diamond in the emerald cut. And yes, that means all of the Chaos Emeralds from Sonic are absolutely wrong, okay? Because they're all based on a round cut instead of the emerald cut. I don't know why, but you know, that's what we have. But there you go. Now you know, go through this and learn a little bit about the cuts of gemstones. Okay, ladies, you might already be familiar with this. Guys, do you ever want to have a significant other in the future? You might need to buy jewelry, in which case you should get to know how gemstones work, okay? Just saying, life advice right here. Know your gemstones. Okay. And then there were more of those wonderful folded paper things, so I just spread those out. There's another one in level 2. There's some more drawing symmetry lines. Level 2 also has this extra fancy bingo cards, which are pretty cool. Okay. Again, it's like explore this and just analyze these pictures and find where the lines of and rotations of symmetry are. Okay. And level 3, same thing, another folding paper, another fine lines of symmetry, this case in dice faces and quilt squares, just like the original example from the text. Okay, so nothing more advanced, it's just extra practice there. All right, any questions about this problem set before I let you go? It looks pretty straightforward. All right, then let's put on some background music and leave you to do the rest. I'll be on standby if you do have any questions.